Consider an agricultural area where two governments share a river. This obviously can lead to water disputes when one group tries to take more than another, potentially leading to a water withdrawal race. If a flood occurs, states need to mobilize emergency response teams. Why would we want two separate states with different teams trying to coordinate a response during an emergency? Flood control infrastructure can make problems worse if they aren't coordinated. Opening up a constriction can push more water downstream, causing problems in some other area. Pollution discharge into streams impacts both adjacent and downstream neighbors, requiring federal laws to prevent states from impacting each other. Pollution gets more complicated as different states often have different laws governing water quality. This problem is so pervasive that attempts have been made to write legislation that applies to watershed boundary conditions, disregarding the political state-level boundary conditions that made water management such a complicated task. So why then do 44 out of 50 US states use rivers as part of their boundaries, and one of the 6 that doesn't is Hawaii? I think in an era of fur trappers, this might have made sense, but we've got bridges. We can cross these rivers. Let's try and do a little better. Let's take some hydrometeorological data sets, and we're going to see if we can come up with new state boundaries using k-means clustering. Step 1 in creating new state boundaries is to just collect some publicly available data. These data sets contain daily records of temperature and precipitation for the US, and you can see here temperatures changing and storms tracking up from the Gulf or from the west across the US. The data that we're going to be using is coming in the form of a NetCDF, and it's going to be a three-dimensional matrix, where along this dimension we have latitude, on this dimension we have longitude, but then it's also going to be stacked up, along this dimension is time. So if we were to take a single pixel from this data set and essentially slice it out, what we would get is one location through time. We can then take all of this and compute the average and use that average to represent mean annual precipitation in our data set. We can do the same exact thing for mean annual temperature. The way the algorithm works is we're going to plot our variables of interest against each other, and then we're going to place candidate starting points in this parameter space. We can then assign each point to one of the two candidate clusters. Once we know which cluster each point belongs to, we're going to compute the distance between each point to their cluster centroid. We can then repeat the algorithm by moving the cluster center points, recomputing the distances, and seeing if this improved the definition of clusters or made it worse. This process repeats over and over and over again until it stabilizes. Every dot on this graph represents a pixel somewhere in the US from our input climate data sets. There's some areas that are very warm, others are very cold. Some areas very humid, others very dry. The k-means clustering algorithm doesn't know where these points are. All it knows is how similar each point was in terms of temperature and precipitation to every other point. So we use the algorithm to split this up into 10 different regions. We're going to then take these clusters, apply them back to our pixels, and we can look at a map of where k-means clustering thinks the state boundary should be. And here are the hydrological states of America. We asked for 10, so our states are bigger. What's really interesting is that these climate-defined boundaries seem to define cultural differences across the US. So here in the northeastern US, we've got New England is kind of split up into a couple different sections. First, they're taking Maine, New Hampshire, and Vermont, and the eastern part of New York and calling those a state. And I think this makes sense because Massachusetts and Connecticut culturally are a lot more similar to the megalopolis that expands from DC and Virginia all the way up through Philadelphia, New York City, and Boston. So these coastal areas are really clustered together into one state, and that stretches all the way out through Oklahoma, sort of this mountainous region. We've got another state here that is the western side of Pennsylvania, stretching all the way through to the middle of Kansas. And this is sort of the farming district of the U.S. Philadelphia probably should be the capital of New Jersey, and Pittsburgh is the gateway to Ohio. So the fact that it's split Pennsylvania right here, I think is amazing. Down here, we've got sort of this like southern coastal region, and really interestingly, the lower end of Florida is pulled off into its own state, and I would call this one Hurricane-Sylvania. Texas was originally its own country, and Texas spans really 3 very different climate regions. So this reinforces the idea that Texas probably should not be one gigantic state. We've got a state that is the Great Lakes, which I think makes perfect sense. And then the West is really divided up in an interesting way. The western mountainous region right here, grabbing North Dakota, Montana, Wyoming, and most of Colorado, parts of Idaho. And then we've got like this Great Plains region here. Some deserts, kind of splitting apart Arizona, Nevada, and Southern California. And then when you get to the West Coast, it gets really wild, where the algorithm doesn't really pull out these nice contiguous pieces, but rather we get this really segmented series of tiny little divides. And that's because of stark elevation changes when the atmospheric moisture is moving, tracking across the Pacific, and it makes landfall here on the West Coast. You get a lot of rainfall right in this region, and then a lot of aridity right on the other side of these mountain ranges. And there you have it. Those are the hydrological states. Have a good day.